Okay, in 2.1, you did a lot of algebra for me. You had limits on everything, you were doing x plus h's in places of x's, and you were subtracting things and dividing and eventually plugging numbers in, and it's a lot of algebra. 2.1 is very algebra intensive, okay? The beautiful thing that happens from difficult mathematical operations is that over time people start to realize there's a pattern in what's going on, and I could do this in a shortcut kind of way. Okay, you've probably had it happen to you in your math before. You're like, hey, look. So I've been working, for example, with my 10-year-old, and we've been talking about multiplication by nines, right? Multiplication by nines has a lot of really cool, like, catches where you're like, oh, I can always know if I get it right because the two numbers, when you're doing single-digit multiplication, the two numbers always add up to 9. Think about it. Like 9 times 8's what? 72. And what's 7 plus 2? 9. Like, you get some cool stuff that comes out, and she does this all the time with her hands, yeah. So there's like a hand trick, and there's just all these really cool ways of simplifying things when you do them enough. So what comes out of section 2.1 is what's happening in 2.2. So 2.2 is not magic. 2.2 is simply what happens when you do enough of 2.1, but I'm not going to make you do enough of 2.1 to figure out all of the cool shortcuts yourself. So that's great, right? So here's the deal. What you did in 2.1, I'm going to ask you a question about that on the test. You're going to have a question about that on the quiz. I mean, like, you're going to have to do it, but you're not going to have to do a whole bunch of problems like that. You're going to do like one problem like that. And then after that, you're going to be able to use what we call simple derivative rules. So there are some wonderful simple derivative rules. These are the first 3, and then there's 3 more that we're going to do today. And then we're going to get into some more complicated derivative rules on Friday and Monday and Wednesday next week. So the first very cool rule is that when you take the derivative, or you look at a constant value, right, the derivative of a constant, you actually, whoops, didn't change my pen, you get 0. And if you think about it, that should make sense. This is an equation, for example, like y equal to 4. What does that equation look like? What kind of line? You're drawing it, say it in words. Horizontal. It's a horizontal line. What's the slope of a horizontal line?
0.
It's 0. Right? So this makes sense. The derivative of a constant is 0. I don't have to do any of the limit stuff. It's going to be 0. The next one, 2.3, is the power rule. So if you were to, my husband had calculus. He was in your position. He took it twice. Okay, he took it twice in college, actually. He didn't do so well the first time, and he decided he needed to retake it. This is the one and only one thing he remembers right now, 20 plus years later from calculus. This one right here. X to the n. The derivative of x to the n is nx to the n minus 1. So visually, what's happening, right, is that the power n comes down as a coefficient, and we decrease the power by 1. And the cool thing is, it works no matter what n is. With one exception, it doesn't work when n is equal to -1. We'll talk about that in Calc 2 for those of you who get to there. But we won't see it in this semester. So everything you see will be able to be used. So it works for fractional exponents. It works for decimal exponents. It works for negative exponents. It works for them all. Okay? So it doesn't just work for numbers like 5. It works for all numbers. Theorem 2.4 is one of those places where you're like, it does what you thought it should do. When you have a number, a constant, multiplied by one of these other rules, you just multiply the constant along. I like to say that it comes along for the ride. The c doesn't affect anything. You just take the derivative of the other piece and multiply it by whatever the c was. Okay? Beautiful things happen. I'd like to sort of insert here one. Your book doesn't identify it as a separate rule, but sometimes people look at it and they kind of freeze up a little bit. And in particular, what happens if you have an equation that looks like this? You guys know what that's an equation of. What is it? It's a line, right? It's a line. So this is a combination of a few different rules. But what I want you to recognize and remember that we've talked about is that derivatives are slopes. So if you have ax plus b, what's the slope of that equation? A. So anytime in particular, we'll talk about the b part's 0 because of the constant rule up here, right? I mean, that's what's going on there. But the derivative of ax, if you just have a linear function, ax is just a. It's actually a special case of number 2.3. I'll show it to you, but it's kind of not necessary. This is a value of 1, right? The 1 multiplies by the a, and if I take 1 minus 1, I get 0, and what's anything to the 0 power? It's 1. So it's a special case of 2.3 here, but really, it's just a line, and we know the slope of a line, right? It's the multiplication factor in front of x. All right, so I kind of jumped the gun and didn't show you theorem 2.5 before I kind of mentioned it in the last one. When you have addition or subtraction of two different pieces that you're supposed to take the derivative of, kind of like that last rule, 2.4, where I'm like, it just does what you want it to do. Here, it just does what you want it to do as well. You just take the derivative of each piece independently, and then you add or subtract it the way it was before, whatever was there before. So you just treat them as two separate pieces of the problem. I'm not exactly sure why your book does this, but it throws the sine and cosine rule into this section as simple derivative rules. They are simpler than the other trig functions. I kind of wish they just put all the trig functions together, but they don't. So for now, these are the ones we have. The derivative of sine is cosine, and the derivative of cosine is negative sine. So they have sort of this relationship that oscillates, right? Sine goes to cosine goes to sine, and if you were to repeat it, the sine would go back to cosine, and the cosine would go back to sine. And they just have this sort of a cyclic relationship, kind of like the fact that these are cyclic functions anyway, right? Sine and cosine, right? They have these wave patterns that just continue, and their derivatives do the same thing. Yes, sir?
Is that a negative sign for that?
It is.
Okay.
Mm-hmm. Yeah, and to be honest, when I was learning calculus, this is the only one that I would ever remember. Derivative of sine is cosine, because then I could just remember the other one was the opposite sign. So this is the one that I remembered, and then every time I needed the other one, I was like, oh, it's the other one. So for what that's worth. So what we're going to do for the rest of class then today is that we're going to take some examples, and we're going to take derivatives with these rules. Okay? So there's not a lot of work to show. Sometimes you might want a step or two of like the simplifying the mathematics, like multiplication or something. There's really not a lot to show in these problems. So it's not going to take you very much paper if you're working through this, right? That's going to be lovely. All right, so here's your first example. Y equals x to the 7th. So can you identify which rule it is, looking at the ones above that we had? It's the power rule, exactly. And so the power rule says, by the way, notice that I'm going to put notation every single time, y prime, right? Don't just put equals. It's not equal to what was before. It's the derivative of what was before. So it's y prime equals. Okay, so what does the power rule say that x to the 7th will have as its derivative?
7x to the 6th.
Right, 7x to the 6th. Very good. All right, is everybody good with that? Make sense? Lovely. Okay, number 2. Number 2 looks like there's multiplication, right? I mean, it looks like these two pieces are being multiplied because they're right next to each other. I mean, and they are being multiplied. But pi is a number, yes? We don't particularly like to think of it that way because it doesn't look like our, 10 digits, but it's a number. So since it's a number, we're actually in the rule that says it's a constant multiplier. The number pi has no effect on what you do when you take the derivative. It comes along for the ride. So I can rather just write it down and ignore it. So I'm finding f prime of t. What is the derivative of cosine of t? Negative sine t. So I'm going to actually write this out this way, just to remind you. That's where it is. But we're going to put the negative in front. So this is negative pi sine t. A word of caution, because I've had several people in my office or through email asking questions about something like this. I don't really care on your homework that's written or on notes or things that you do or what you turn into me in printed form, whether you change your t's to x's, but WebAssign really does, okay? If you put this, that this is going to be negative pi sine x, it is not going to count you right. Okay, so make sure that whatever variable WebAssign starts with, you give your answer that way as well, or it will not understand what you're talking about. Okay, it's a syntax problem in WebAssign, okay? So this is negative pi sine t. Any questions about that?
Yeah, so is that the sine, cosine, and the constant multiplier?
Yes, it is. There's two rules at play there. And in fact, as we move in every single problem that follows, you're going to see more than one rule at play. Yeah. So there was the constant multiplier rule with the pi, and then there was the sine, cosine rule as well. All right. Sometimes the problems that we begin with don't look like one of those 4 or 5, whatever rules that we had before. You have to change them into a different form in order for you to identify which rule it is that you're going to be able to use. So in particular, I have an x squared here, and that's fine, but none of my rules told me what to do when I have a variable in a denominator. Agreed? So we have to use some algebra to change the way it looks right now in order to be able to use the rules that we already have. So in particular on this one, the 3 doesn't move. Don't go moving my 3 anywhere. It is in the denominator for good. But the x squared can move. In particular, it can move from the denominator up to the numerator if I change something. What would I have to change? The sign of what? The 2. I need to change the sign on my exponent. So I'm going to write this. You can write it in the numerator if you want like that. Or you can write it just out beside like this. It doesn't matter. Okay, so is everybody okay with that rewritten step? It's property of exponents. You've seen it a long time ago. You encounter it usually somewhere in middle school. Okay?
Sorry.
The cool thing is that once I get it like that, it actually looks like some rules that I have. Okay? There are 2 rules here that are going on. What rules do you see? Constant multiplier and power rule. Does everybody see that? Okay, so the constant multiplier rule says that I'm going to be able to simply rewrite the constant 4 over 3. Right? Yeah, 4 over 3. And the power rule says that the x to the negative 2 can be written how? What's the derivative of x to the negative 2? Okay, so negative 2 first, right? Because it's negative. Is it x to the negative first or x to the negative third? It's actually negative third. Yeah, so you have to remember that the subtraction doesn't always make things look like a smaller digit, right? Because we're dealing with a negative number on this one. So when I have the negative 2 minus 1, I actually get negative 3. When you take your gateway exam for me, which is coming up, I think, let me just see the when so I don't say it wrong. It is next, today's the 18th, yeah, so it's next Friday. You're going to take the derivative quiz in class. The derivative gateway, the derivative quiz, gateway quiz, whatever we're going to call it, is 20 questions. And it's 20 questions that are all find the derivative, find the derivative, find the derivative, find the derivative. That's all it is. And on that quiz, you don't simplify anything. Yeah, that's fantastic. So you would leave it just like this, where it says differentiate, you'd be done. Okay? Now, on everything else, I want to know that you can do the because the whole point of the derivative quiz is do you know the calculus? Do you know all the calculus rules and can you apply them properly? Okay, so we'll deal with the algebra, in other situations, but on that quiz, it's just all about just the calculus rules. As we're doing homework, as you're doing WebAssign, as you're doing quizzes, as you're doing exams, you don't stop here. You will stop when your answer looks like the original question. So notice in your original question, there weren't any negative exponents. So we're not going to have negative exponents in our answers. Okay? We're not going to stop and not deal with the fact that this is 4/3 and a negative 2. We're going to multiply those together because we can multiply. There's nothing wrong with doing that. So we're going to do the multiplication. Okay? So those are the 2 things that we have to do to actually simplify or clean this problem up. So we're going to take the negative 2 times the 4/3. So that's going to give me negative 8/3, right? And then the x to the negative 3, how do I get that to have a positive exponent again? I put it back into the denominator, and what will its exponent then be? 3. Okay? So there's nothing terribly complicated about the algebra step. I just don't want the algebra to be the reason that you're not getting through the gateway. The gateway is all about calculus. But for all of your homework, you're going to simplify that last piece. Okay. Now, some of your questions actually do this. They put this like table in here where they tell you, rewrite it, then differentiate it, then simplify it. But eventually they realize you should be able to figure out that those are the steps you need to do anyway without them creating a table that forces you to plug them in these little boxes. So you get problems like this. So in this problem, what you see happen is you see again a denominator situation, right? But you've got stuff in the numerator and stuff in the denominator, correct? So you can't just pull this thing up. Because if you do, then you're going to have products, right? Things that are multiplied that aren't constant multipliers. They're variable components that are being multiplied. That's not cool. So there's a couple of different things you could do. I'm going to show you the one that I feel like is the most natural from here. And then I'll show you another option if you happen to think of it a different way. The most natural from here is to recognize that you can rewrite this where each of the numerator pieces has the denominator x squared. Now, it's a fact about fractions. Usually we use this fact in the other direction, right? You get common denominators and you add fractions together, right? So these all have common denominators. We can combine them back together and get back to where we started. But you can also separate them back out. It's just using that property backwards. The reason that's nice is because some of this simplifies so very nicely. What is x cubed over x squared? It's just x. What is 3x squared over x squared? It's just minus 3. Now, the last piece doesn't have sort of this cancellation portion of the idea going on, but it can still be rewritten much like the last problem we did, right? How can I rewrite 4 over x squared so that I can use the rules that I have? Yeah, 4 and then x to the negative 2, right? I can pull the 2 up to the numerator, pull the x squared up to the numerator and make the exponent negative. Is that good for everybody? You all right? You're good. Okay, just making sure. One of the things that's wonderful about teaching the iPad is I can watch your faces. So when you guys start to look confused, I'm going to ask you. I'll be like, okay, are you really okay? All right. We have not done any calculus yet, right? This is all algebra. So don't forget in the middle of doing the algebra to actually finish the calculus part of your problem. So this is the same g of x that I started with, just written differently. And I still need to take the derivative. All right. So here's that piece that I mentioned sort of in the middle of my steps. And I said, here's sort of an extra little rule that they don't really address. It's sort of hidden in here. What's the derivative of x? 1. How come, Jared?
It's the same formula. It's just like x of 1 to be multiplied.
You can think of it that way. So if you want, you can pull the 1 down in front. X to the 0 is 1, and it goes away. Is there another way to think of it? Nope, there's not. There is. What is this equation an equation of? A line with a slope of 1. That's why. Okay. Remember, derivatives are slopes. Y equals x. That portion of this is linear. The whole thing's not linear, but the portion with the x in it is linear. Okay, so whichever way you like it, that's great. How about the negative 3? What's the derivative of negative 3? 0. I'm going to put 0 in here just to remind us that we did it. If you leave it out, that's fine too. I'm going to rewrite the steps at the end, and it won't be there. How about the derivative of 4x to the negative 2?
8x, negative 8x to the first.
Close. Negative third. Yeah, negative third. Okay, so you did a really good job in recognizing that there's 2 pieces going on here. I've got the constant multiplier and I've got a power rule. and they're both going to come into play, right? So the 4 is going to stay, but the power rule says I'm going to take the -2 and multiply it by what's there. So that's actually giving me my -8. And then again, we've got that negative exponent thing going on, right? So when I subtract the -2 minus 1, I get -3. Okay? Gateway, you're done, right, at this step. If you're doing your homework or anything else, you're not done. You're going to clean it up. And I'll give you a couple options of how it can look like when you're done. Obviously, we don't need the 0. You can just write the 1. The 8x to the -3. Well, that's -8 over x cubed. And I'm okay with you leaving it like that. There's nothing wrong with that answer. It's perfectly fine. If you were looking at like a problem written by somebody else, or if you were using an online resource, they might get a common denominator and put these back together. You don't need to do that, but I just want you to look at, if you were looking at somebody else's answer and you were like, oh, I got it wrong. Maybe you didn't. Another equally right answer here would be x cubed minus 8 over x cubed if you get a common denominator. Okay? They don't look the same, but they are different versions of the exact same answer. All right, next one.
Okay, on the second, answer that you wrote,
Yep,
so the x cubed cancel.
it would, but then it would be right back to this version.
So you just
So like you can't cancel this because that's canceling terms. Terms don't cancel. Factors cancel,
Okay.
but terms don't. So if you tried to cancel, the only way you could is by making individual fractions, and then you'd be back to the first way that I wrote it. Just, yeah. I have no desire for you to do this, by the way. That's not my goal here. I just want you to recognize if you saw somebody else give that answer, like in an online resource you were using, I don't want you to feel like you did something wrong. Okay, there's an equally good chance that there's just a different way of writing it. Oh my goodness, radicals. I didn't tell you what to do with radicals, did I? But I mean, it's in this section, so there must be something we can do. Does anybody know how you can rewrite radicals in a different way? Fractions, can you be fractional exponents? There we go, there's the word. Fractional exponents. So what would the cube root be? Right, 1/3. And what would the fifth root be? 1/5. And just for the sake of having talked about it, what if I have the fifth root of x squared? What would that be?
2/5.
Right. So if there's an exponent on the factor underneath, right, then it actually becomes a numerator in the fractional exponent. Okay, so let's go back to our problem now. That's an irrelevant. It's not irrelevant. It's just not pertaining to a particular problem. Once it's written with the exponent form, this is an example of one of those ones that I told you. It doesn't have to be nice, neat whole numbers, right, as exponents. We've encountered negatives a couple of times now, and now we're encountering fractions. So the fractions have the same way of working with them as power rules as the whole numbers and the integers that we did before. So what would x to the 1/3 derivative be?
1/3 of x to the 1/3 minus 1.
1/3 minus 1. Do you guys know what that is? Negative 2/3. On your gateway, if you want to write 1/3 minus 1, you can. That's fine. On everything else, you should definitely have resources there to just go ahead and find out for me that it's negative 2/3, even if it takes you a quick second to do so. How about x to the 1/5? 1/5. To the what? Negative 4/5. Good. Negative 4/5. Does anyone have any questions on that so far? We're not done, but is that okay so far? Okay, so you were hoping we were done. Why are we not done? Needs to be the same form it started in, right? I know, it's terrible. Okay, so it started with radicals. I need to put it back in radical form. But at this point, I've also got the issue that they are negative, correct? Okay, so the negative means I'm going to go to the bottom. And radicals are going to go back the way that we came, right? Put that back in radical form. So I'm going to have this x to the 2/3 in the bottom, which is the cube root of x squared, right? The 2 stays on the x. Cubed becomes the cube root. The 3 becomes the cube root.
Is the exponent on the x outside the radical?
It doesn't actually matter. It's the same thing. So if you put it underneath like this, or if you put it outside like I had originally written it, it's exactly the same meaning. So you don't need to worry about that. I think probably people tend to keep them underneath the radical more often. How could I rewrite the 1/5 x to the negative 4/5? What will that one look like? I think that's what you guys are telling me. Does that look right? 5/5 root of x to the 4th. And there's buttons in WebAssign that let you do index the different indices on the outside of the radicals and all that kind of stuff. So if you're having trouble finding those, let me know, but they're there. Okay, number 6. Back to a much nicer problem, right? Y equals 3x cubed minus 10. Directions change slightly. This one actually asks us to find the slope of the graph of the function at the given point, and then use the derivative feature of a graphing utility to confirm your results. So the given point business is the new part, and you see we've got a point listed here, 214. Yes? Okay, so let's find the slope. That means the same thing, right? Find the slope is the same thing as saying derivative. Okay, so what is the derivative of 3x cubed? 9x squared. And what's the derivative of the negative 10? 0. Right? It's 0. So this is it. This is, after all the hard ones, you're like, well, that's it? Yeah, it's it. But it says to use the derivative feature. Oh, wait, before we get to that, I missed the second part of directions. It says of the graph at the given point, right? And what's the derivative at the given point? Well, here's your given point. So what do you think we're going to do with it? Plug in the x value, exactly. We're going to plug in 2. So we're going to actually find what happens when x is equal to 2. So what is 9 times 2 squared? 36. All right, using the graphing utility to confirm your results. So we're not going to finish this today, which is fantastic for you. It means we're going to push everything back. But let me show you the graphing utility stuff, and we'll stop today. We'll pick up with this next class period, and we'll push your quiz to Monday. How does that sound? Yeah, good? Okay. This won't be due on WebAssign until Monday as well, so I'll push that back. If for some reason you're starting to work in WebAssign and I have failed to go out and change that because once I leave here I'm headed out off campus, I might forget, just somebody send me an email and remind me. Okay, grab your calculator out. This is such a cool feature and you're so going to want to know how to do it. Promise you. Put the equation, it was an easy one, the original equation into y1. Original equation. So that was x cubed minus 10. Put the original equation we were given, x cubed minus 10, into y1. Everybody do that. X cubed minus 10. And then go out of the graphing screen. Just get into your regular blank screen. There is a wonderful button that you definitely need to know about. It is the math button. All right, when you pull up the math button, it gives you lots of little options. It says frac, decimal, cubed, cube root, x root, f min, f max, and if you go down one more to option number 8, what does it say? Inderiv. It's option 8, by the way. Inderiv. Choose that one. Depending on the operating system in your calculator, it will either write inderiv on your screen. That's what mine does because I have an older version of your calculator. Or, yours is definitely not older. It's going to give you notation that we haven't discussed yet, but it looks like this. There's a little box here. There's parentheses with another box inside. And then there's a line, and there's a box equal to another box. All that. Okay? So I want to show you, depending on which of these you have, what you do next. So let me do mine first. If you have my version, you need for this to say y1, comma, x, comma, and then your x value, which is 2. Okay, so how do you get y1? Everybody needs to know how to get y1. Y1 you hit by hitting vars, y vars, function, y1. Okay? So that's what it looks like. If you have this other version, okay, the Success Center knows how to do all this too, by the way. They've all had me or somebody else who tells them this, okay? If you have the other version, what do? Well, you put an X here. I'll do it in red, actually, so that it stands out. You do an X here. You put the y1 here. And you put the 2, because ours was at x equal to 2 in the last part. So you put all the same things in, just in different locations. And when you hit enter, after you've done that, what does it say?
36.
It says 36, which was the answer you got.
How did you get the Y1 from there?
You hit vars. There's a button that says VARS, vars, Y vars.
This?
Yep, and then function, hit enter, and Y1. All right. We'll pause there for today.